We'll begin the mathematical part of the course. Lecture 7 is all about developing the mathematical rigor for trying to come to terms with the question of how long does it take for a particular algorithm to execute. This is important for computer scientists and for software developers. It really is important to be able to analyze algorithms, not just acquire, a large, not to just amass, a big collection of algorithms to do things. Okay, here's a question. How long does it take to sort an array of size n using bubble sort? All right, the answer is there is no answer. This question is not well stated because algorithms by themselves don't take any amount of time. What actually takes time is a computer program, and the amount of time that a computer program takes to execute depends on a lot of details, including the speed of the central processing unit in the computer, various hardware aspects as well as software aspects. How was the code written? How was it compiled? And so forth. Nevertheless, the question is an important question. And while it can't be answered with a precise answer, a definite numeric answer, we can talk about how long it takes bubble sort to sort in a way that is, well, not complete in a sense. Still, we can give an answer that is meaningful and mathematically rigorous as well. All right, before we look at the sorting algorithms that we've been discussing and develop a rigorous way of analyzing them, let's start with a more basic, a simpler bit of code. So here's something that you may have done in your introductory programming course. You may have done exactly this or something quite like this. Let's look at this code. So this code basically has a nesting of two loops. The outer loop loops n times. I'm assuming some value for n is specified beforehand. So the outer loop loops n times, and the inner loop also loops n times. Every time through the inner loop, let's assume that a single asterisk is printed. So of course, in the Java world, that would be system.out.print, parentheses, double quotes, asterisk, double quotes, parenthesis, semicolon. And for C++, it would be cout less than, double quotes, asterisk, double quotes, semicolon. Okay, but anyway. And then after the inner loop, let's assume that a carriage return is printed. Okay, so as I say, you've probably done this sort of thing, and whether you have or you haven't, this is the kind of thing you get. You get n rows, each row containing n asterisks. So for example, if n was 5, you'd wind up with this 5 by 5 pattern of asterisks. Okay. So here's some concrete questions that we can ask and answer. Well, actually, the first question here is too vague again. How long will it take to execute the code? Yeah, once again, that depends on the computer, on the way the program was compiled, and things like that. And it depends on n, of course. That of course is very important here. We're going to get very focused on the dependence of n on n. Here's a very rigorous question. How many asterisks are printed? So you should realize that the number of asterisks printed is n squared, right? N rows, n columns, so n squared asterisks. On the previous slide, n was 5, and there were 25 asterisks. Yeah, now that's the same thing as saying that the number of times that the inner loop's body is executed is n squared. And you see that because every time through the outer loop, you go through the inner loop n times, right? And of course you go through the outer loop n times. So n times n is n squared. Okay, we do not know, we cannot say in general how long it takes to execute the inner loop's body one time. So in the program we're looking at, that means how long does it take to print a single asterisk. That's going to depend on the computer. Nevertheless, it's a constant for any given computer. And any given program, after a program is compiled and running, there's some constant associated with the amount of time it takes to print that single asterisk. So if we call that constant capital A, and I don't care if it's measured in terms of seconds or milliseconds, it makes no difference, some constant. If we take that constant and multiply it by the number of times we actually execute the inner loop's body, number of times we print asterisks, n squared, then that product, a times n squared, is going to be the total amount of time spent executing the inner loop's body. Now there's some other code here. There's code that is inside the outer loop, but which is nevertheless is not inside the inner loop. Okay, so inside the outer loop, but outside of the inner loop. In this program, that would be the code for printing carriage return, right? The carriage return occurs after the inner loop, but it's still inside the outer loop, right? So therefore, that code is executed n times. If capital B represents the amount of time to execute such code during a single pass through the outer loop, then the total amount of time executing such code is going to be B multiplied by n. In addition, there can be some code that is not inside either loop, that's outside of the outer loop. And if you go back and look at the program, you might feel like, well, there is no such code in this particular program. But actually there is. There's it's a little bit hidden from you. The initialization part of the inner loop sets I equal to 1. Or is it 0? I forget. But anyway, that initialization of I occurs just one time. It does not occur inside the loop. In addition, you could toss in some time that might be spent by the operating system to set up the program. Maybe the time required to load the program into memory and so forth. Anyway, if we account for all that time, it's a constant amount of time. So let's call that constant amount of time capital C. And of course, there is no dependency on n here at all. That code is executed just in a constant amount of time. Okay, but we've now accounted for all of the time spent to execute the program. And we can put it together, and here it is. Okay? We've got the amount spent inside the inner loop, which is capital A times n squared. We've got the amount of time spent outside of the inner loop, but still inside the outer loop, which is capital B times N. And then we have some constant time in addition. Okay? You put it together, and of course recognize that capital A, capital B, capital C are some constants, even if they're not known. We could this as a polynomial in N, a quadratic polynomial in N. Henceforth, we're going to allow ourselves to think about N as something that varies. Okay? We're going to be interested in particular in how this grows as N gets bigger and bigger. Okay, so there it is again. We're thinking about that as a quadratic polynomial in N. Now, we don't really know the constants A, B, and C, and we really don't want to focus on them. We really agree that they're different constants for different computers and different operating systems and different compilations of the program and so on and so forth. So people recognized this a while ago, and what they did was they drug out some very old established mathematical notation, which we nowadays call Big O notation. And Big O notation is good for expressing the rate at which something grows. Okay, like this polynomial capital AN squared plus capital BN plus capital C. We want to capture a sense that it's a quadratic, and well, not to give it away too fast, but we're going to wind up saying that polynomial is capital O of N squared. We'll figure out what that means as we go along here. Okay, so what does it mean? Well, it means something very definite. It means that polynomial capital AN squared plus capital BN plus capital CN stays smaller than a constant multiplied by n squared. Some constant multiplied by n squared as n gets bigger and bigger and bigger. Okay? We'll get a little bit more detailed about this as we go. Let me say exactly what the claim is when we say that this polynomial is big O n squared. The exact claim is this: as long as n is sufficiently big, okay, greater than or equal to some value, which we can not worry about how big that has to be. Okay. That capital A times n squared plus capital B times n plus capital C will always stay less than or equal to capital D times n squared for some constant D. There is some constant D. It depends on A, B, and C, but it will always be true no matter what n is, as long as n is sufficiently big. Okay, that's rather a very precise statement, and here's a very precise proof of it, which I want to point out right away. The kind of proof that I'm going to give right now is not something that I'm going to hold you responsible for doing. Okay? I'm going to make a proof of my claim, and all I have to do is assume that n is at least 1, greater than or equal to 1. Which is very, not a big deal. What I'm going to do here does not work if n is 0, but it doesn't matter. Okay, the actual time is A times n squared plus B times n plus C. Let me define a constant capital D equal to 3 multiplied by A plus B plus C. Okay? So now I can go like this. a times n squared plus b times n plus c is less than or equal to d over 3 times n squared plus d over 3 times n plus d over 3. Well, how come I can do that? Well, because d over 3 is a plus b plus c. And of course, I am assuming that a, b, and c are non-negative, all right? They're probably positive, but in any case, they're not negative. So d over 3 is greater than, d over 3 is equal to a plus b plus c, and that's greater than or equal to a. It's also greater than or equal to b. It's also greater than or equal to c. So for that reason, I can make this first step. The original polynomial is less than or equal to d over 3 times n squared plus d over 3 times n plus d over 3. All right, now n is less than or equal to n squared. That's certainly correct. As long as n is at least 1, it's certainly true that n is less than or equal to n squared, and also 1 is less than or equal to n squared. So I can continue and say that what I've done so far is less than or equal to d over 3 times n squared plus d over 3 times n squared plus d over 3 times n squared. And all I'm doing there is adding the same thing 3 times there. So I got 3 multiplied by d over 3 n squared, which is equal to d times n squared. So what I've done is proved that an squared plus bn plus c is less than or equal to dn squared. And that's the formalism that allows me to assert that capital AN squared plus capital BN plus capital C is capital O N squared. All right, now, do not get thrown by the notation. The capital O is very special notation. It looks like this says that we have a function named capital O evaluated at n squared. But capital O is not a function. This notation is not a function, and capital O n squared, well, it represents something that is growing no faster than a constant times n squared. All right, we're ready to actually look at the sorting algorithms, beginning with bubble sort. What we'll do is we'll look at bubble sort and selection sort. We'll wave our hands at insertion sort. And later in the next part of this lecture, we'll go on and consider merge sort in some detail and quick sort in less detail. Okay, so we're going to establish the claim that bubble sort takes capital O n squared time to sort. Even without a careful analysis, you can at least get right off the bat some kind of sense of why this might be. We just got done looking at an example of a little bit of code that printed a little block of n by n asterisk, and we decided that that took capital O n squared time. And we reasoned that out, and it very much depended on the fact that we nested 2 loops together here. Okay, that code had an outer loop that looped n times. It had inner loop that looped n times. And the upshot of that was that it took a constant times n squared plus a constant times n plus a constant amount of time. And we sort of sweep all that up and say that it takes big O n squared time. All right? Well, it's the same thing is going to be true of bubble sort, but there is a little subtlety here. So difference is, okay, the outer loop only loops n minus 1 times instead of n times. That is a very superficial thing, particularly as n gets bigger, as n gets large, the difference between n minus 1 and n really doesn't make any difference. Okay, but more significantly, the number of times that the inner loop loops depends on which pass we're making through the outer loop. Okay, in our simple asterisk example, the inner loop looped n times. But, and now go back and think about this, it was stated very precisely on a slide in the bubble sort notes. How many times do we go through the inner loop? Well, on the first pass through the outer loop, we go n-1 times through the inner loop because there are n-1 comparisons. Okay? Let me say it again. The first time for the outer loop, the inner loop is executed n-1 times because of the n-1 comparisons during that first pass through the array. The second time through the outer loop, which means the second pass through the array, there are only n-2 comparisons, and the inner loop executes only n-2 times. Okay, and so on and so forth. Finally, on the last pass through the outer loop, the inner loop only loops one time. If we add these things all together for a particular, all right, adding this together, we get n-1 plus n-2 plus n-3 ... down to 3 plus 2 plus 1. Okay? So rewriting that in the opposite order, all we're doing is adding 1 plus 2 plus 3 plus 4 ... up to n-1. Okay, we're just adding all the integers up from 1 to n-1. I'm assuming here that n is at least 2 so that makes sense to you. But if you can assume n is bigger than 4 if you like, so it really looks right to you. But anyway, it doesn't matter. If you add up the numbers from 1 to n-1, there's a formula, well-known formula. You may have seen it in a math class that amounts to saying that if you add the numbers from 1 to n-1, that is the same thing as n multiplied by -1 divided by 2. Okay? You can check that on your own for a couple cases. Well, let's do one real fast. If n is 5, then we're adding 1 plus 2 plus 3 plus 4. What is 1 plus 2 plus 3 plus 4? Okay, well that's 10, isn't it? Right. Well, n is 5, so n times n-1 over 2, that's 5 times 4 divided by 2, and that's also 10. Okay, the formula is correct, and we're not going to prove it. So now just do a little algebra, and you'll see that by distributing through, the expression that we just obtained is the same thing as 1/2 n minus 1/2 n. So that right there is exactly the number of times that we will go through the body of the inner loop for bubble sort. Okay? Well, let's pause and remind ourselves what happens during the execution of the body of the inner loop. Okay, in bubble sort, that consists of two consecutive numbers in the array and then potentially swapping them. All right? So we're ready to analyze bubble sort along the same lines that we previously used for the asterisk printing code. And it basically goes like this. Let's let capital A be the amount of time spent on a single pass through the inner loop of bubble sort. Well, already there's a tiny issue here. As I just got done saying, during a single pass through the inner loop of bubble sort, two numbers get compared, and then they might or might not be swapped. Okay? All right, so the amount of time spent doing that actually depends on whether they are or are not swapped. And what I want to do here is take up the worst case analysis. Okay? In the worst case, every time through the inner loop, the two numbers are compared and then swapped. All right? So let's let capital A then be the amount of time it takes to compare two consecutive numbers in the array and then swap them. Okay? Since we're doing that 1/2 n squared minus 1/2 n times, the total amount of time spent inside the inner loop is basically, or at least is not any worse than, capital A times 1/2 n squared minus 1/2 n. All right? All right, let's think about the rest of the code. So there's the time spent inside the outer loop, but outside of the inner loop. Okay, let's let capital B, as before, be how long it takes to take a single pass through the outer loop, excluding the time it takes to do the inner loop. Okay? Since we're doing all of that n minus 1 times, the total amount of times to do all of that code is capital B times n minus 1. All right? And then, like before, we toss in a constant amount of time, capital C, to account for anything that's spent either before the outer loop, well, let's say before the outer loop, and or time spent doing stuff after the outer loop. Okay, if there's anything. Doesn't really matter. Just add a constant. There it is. So, now, you simply take what we've just derived and rewrite it a little bit, and you observe that, once again, all it is a constant times n squared plus a constant times n plus another constant. So just like the asterisk printing business, we have a quadratic polynomial in n. And since it's a quadratic polynomial in n, by the same reasoning that we used before, this is no worse than some unspecified constant times n squared. In other words, this is big O of n squared. So reasoning very much like we did with the asterisk printing program, we're able to deduce here that bubble sort requires amount of time that is big O of n squared. Okay? And again, I want to remind you that big O of n squared, big O is not a function. Of n squared means that we're talking about something that is less than or equal to an unspecified constant multiplied by n squared. Okay? Similar reasoning can be used for selection sort and insertion sort, and you'll be asked to check some of the details on this, particularly for selection sort, which is frankly very, very similar to bubble sort. If you go back and look at the lectures for bubble sort and selection sort, you'll see that the number of times through the inner loop for selection sort is exactly the same as the number of times through the inner loop for bubble sort. Insertion sort is a little bit different, but in any case, all three of these algorithms execute an amount of time that is big O n squared. So, when you're ready, when you feel like you understand all this big O notation business, and what has been done in this part A of the lecture on time complexity analysis, then you should go take the self-quiz on part A of time complexity analysis.